So for this video, we are going to go over, like I said, linear and nonlinear transformations. So oftentimes when we are given additional data points or we want to shift or scale our linear function for a multitude of reasons, then we would have to, like I said, we will sometimes want to shift or scale our x or y variables for, we never know when there will be adjustments or when we'll need it. And so in this video, we'll learn how to do just that. Okay, so let's say so going over scaling first, let's say given this equation of income and food expenditure, sorry, we we want to multiply the x variable by a constant of c. And note that we're trying to multiply the x variable, not necessarily the coefficient, which is the 10. And so if we multiply the x variable by some constant, we have to compensate by actually dividing, rescaling the 10 by the same constant. So let's say our if we multiply x by 10, then in this example we'll have to divide the beta 2 10 by 10, right? Because we're multiplying x by 10. So we'll write that as y equals 1x plus 50. And then we'll have to also note that x equals the income that is rescaled to times 10. So we can interpret that as if our income is 100, then it's automatically rescaled to 1,000, but our impact of the coefficient of beta 2 is 1. So in the result, it's still the same. And so when we do that, for the more general model, this is how it's mathematically shown. When we multiply by c, we have to also divide the beta 2 by the same constant. And note that our beta 2 will change even though our overall y output didn't. And so our standard error also changes for the beta 2. Because again, beta 2 and our x variable are have different values. What doesn't change is the test statistic p-value in r squared. And this is because the scaling the x-axis, multiplier dividing it, it doesn't necessarily add any input. It just changes our properties of how beta 2 and x act in relation to each other. Okay, so for the second example, let's try to scale y instead of x. And so when we do that, we'll write that as multiplying y by the constant. And then if we do that, because y represents the entire function, we're actually going to have to multiply every variable here by this same constant. So the intercept and then our x as well as our error. And so what that results in, again, our test statistic, p-value, r squared, all that doesn't change. But our coefficients of beta 1 and beta 2, they will be rescaled to the constant we're multiplying by, as well as our standard errors. All right, example 3. Let's say we scale x and y with different values of cy. So we'll denote cy and cx because we have to keep in mind that they're different values. Obviously, we can just use like two different letters, but for the sake of simplicity in my notes, I'll write cy cx. So factoring both of that, we can write that as y multiplies to its constant, and then beta 1 multiplied by the constant that belongs to y, plus for beta 2, we're actually, when we scale x, beta 2 is impacted by both the constant of y and x. So what we actually have to do is cy over cx, because right here we're rescaling beta 2 when we multiply by the y by the constant, and then we're also doing that for beta 2 when we rescale x. So cycx times beta 2 x. Actually, that's not correct. So cycx beta 2, that's correct. But we also have to rescale the x variable itself, because that's what we did for when we rescaled our x. So we're multiplying the x by the constant, and we're also dividing by the beta 2 by the same constant. And then we can't forget the error as well, because the error influences the y, whereas the rescaling the x variable doesn't necessarily impact the y. So when we do that, the standard error of beta 1 will be the new standard error of beta 1 times, it'll transform into a new standard error where it's multiplied by the constant of y. And then for beta 2, it's cy over cx, because once again, the beta 2 coefficient, is affected by both x and y transformations. But the test statistic, p-value, r-squared, all of those factors for inferencing, those don't change. All right, let's say we want to scale x and y with the same values. So we don't have to say cy or cx. We're scaling both at the same time. In that case, it would look similar to this, except right here, the beta 2, because they're the same values, we can kind of just ignore the fraction here and say this is a 1. So c times y, beta 1 is still multiplied, but because these are the same values for beta 2, we can kind of just ignore that and say beta 2. However, we still have to rescale x by c, because that's what we did for the when we rescaled x, and then the error as well. So only the beta 2 changes because the constants here are the same. And so once again, our new beta 1 is c multiplied by the constant multiplied by the beta 1, as well as our standard error of it. Okay. And so only the beta 1 coefficient and its standard error changes, not the beta 2, because the standard error of beta 2 doesn't change because the coefficient value of beta 2 didn't change at all. Not to be repetitive, but just to make sure. Okay, second to last example, let's say we don't want to scale x and y, but we want to shift it. So if I draw like a graphical representation, if this is our equation, then we want to, let's say we're shifting y, and so we're kind of drawing like a parallel line here. Okay, so if we do that, then it'll be given at the equation will be given as the y times, or not times, y plus the shift equals, the beta 1 is impacted by the shift because it is the intercept, but the slope isn't, so we keep that constant. And so the beta 1 changes in this case, but the standard error of beta 1 does not change. And then the test statistic of B1, because the beta 1 shifted down or up, whichever case, actually does change, but not the R squared, because the R squared is only looking at the factoring in the slope, or the kind of the correlation of x and y. And then for our last example, if we shift x, then we'll get the equation of beta 1 minus beta 2 times s of x. So I'm guessing that there's supposed to be a parenthesis here, not in my notes, but that's what I'm guessing. So beta 1 minus beta 2, if we shift s of x, or I guess that's the intercept. So let me write that again. So beta 1 minus beta 2 times s of x plus, and that alone is the intercept. And then the beta 2 is the same thing because we're shifting and not scaling it. But the x variable itself is shifted by the constant that we decide. And then the error stays the same. So in this case, the test statistic of beta 1, once again, it changes. Since the standard error of beta 1 and beta 1 also changes. So test statistic of beta 1 changes, as well as just the raw value of beta 1, and the standard error of beta 1 also changes. So all of the beta 1s change, but not the beta 2 or the error or the y or whatever, if we just choose to shift x. Well, I guess the x variables also shifted to x, or shifted by our constant, but we don't change the coefficient. So what I said, all that obviously wasn't the most clear. I kind of just winged it, and even if you did get all that, it might be a little difficult to memorize. So this table right here pretty much sums up what I've been trying to say, and also some like new information of the R squared and all that. So R squared, despite no matter how we decide to shift, will not change. When we're rescaling it, you'll kind of see that the t statistic doesn't change either, but when we're shifting to the left or right or up or down, then the t statistic will change. So there are pretty clear trends here, but I think once you understand the general gist of what we're trying to do with regards to shifting and rescaling, then this table is very helpful. And yeah, there's really no need to memorize everything that's going on, because the table does a pretty good job at doing that. Alright, that will be it for this video. Don't really know what I'm going to cover for next video, but it will be uploaded soon. So, but that's it for transformations, linear and nonlinear transformations.